The sleek, silver-white casing of a high-speed charging brick or the ultra-thin bezel of a contemporary smartphone serves as a deceptive mask for a material that defies the fundamental expectations of the metallic world. Within these devices, hidden behind layers of polymer and glass, exists a substance that possesses the visual brilliance of polished chrome and the structural density of a heavy industry component, yet it lacks the thermal resolve required to remain solid in the warmth of a human palm. This is gallium, the 31st element of the periodic table, an object that functions as a physical paradox. While most metals utilized in common tools, such as iron or copper, require the intense heat of a specialized furnace to transition from a solid to a liquid, gallium undergoes this structural collapse at a temperature of only 85.57 degrees Fahrenheit. Consequently, a solid bar of this metal, which appears as rigid and unyielding as a piece of surgical steel, will begin to soften and liquefy the moment it is retrieved from a cool drawer and placed upon human skin. The resulting pool of shimmering liquid silver is not a toxic hazard like mercury, nor is it a product of stage magic. It is a demonstration of a unique atomic architecture that sits at the very edge of stability. The exploration of these hidden elemental properties is a journey into the engineering of the future, a pursuit supported by a global community of observers dedicated to uncovering the mechanics of our reality. Subscribing to the channel and contributing a perspective in the comments helps ensure that these detailed investigations into the substances that build our world continue to reach those who seek a sophisticated understanding of the physical universe. The physical reality of gallium is governed by a state of crystalline fragility that has few parallels in the mineral kingdom. To observe the transition of gallium from a solid to a liquid is to witness a masterclass in the laws of thermodynamics and atomic bonding. Most metals achieve their solid form through a process called metallic bonding, where the atoms are organized in a tight three-dimensional grid, sharing a collective sea of electrons that acts as an incredibly strong subatomic glue. In metals like iron, which melts at 2,800 degrees Fahrenheit, this glue is so powerful that it requires an immense input of kinetic energy to break the atoms apart. Gallium, however, operates under a different set of structural rules. While it is classified as a metal, its crystal lattice is unusually complex, adopting an orthorhombic shape where the atoms do not exist as single independent units, but rather as diatomic pairs. To explain this on the fingers, within a solid piece of gallium, the atoms are paired off, holding hands tightly with one specific neighbor, while only barely touching the fingertips of the rest of the crowd. This creates a loose and disorganized structure. The bonds between the pairs are significantly weaker than the internal bonds of the pairs themselves. As the ambient temperature rises toward 85 degrees Fahrenheit, the vibration of the atoms increases. Because the fingertip connections between the pairs are so fragile, they are the first to fail. The rigid skeleton of the metal collapses, not because the primary bonds are destroyed, but because the secondary connections lack the thermal endurance to hold the pairs in place. This is why gallium behaves more like a block of frozen wax or cold honey than a traditional structural metal. It is a substance that is perpetually on the verge of a phase shift, existing in a state of high energy readiness to abandon its solid form. The sensory experience of this melting process is a departure from common human intuition. When a block of ice melts at 32 degrees Fahrenheit, it absorbs a significant amount of heat from its surroundings, making the hand that holds it feel cold. Gallium follows the same thermodynamic laws, but because its melting point is so close to the temperature of the human body, which averages 98.6 degrees Fahrenheit, the sensation is one of eerie fluidity. As the metal absorbs the internal warmth of the skin, the solid corners of the bar begin to round off, and a shimmering, heavy liquid begins to pool in the micro-ridges of the fingerprints. Unlike water, liquid gallium has a remarkably high surface tension, measured at 718 millinewtons per meter, which is more than 10 times higher than that of H2O. This causes the liquid metal to bead up into perfect mirror-like spheres that roll across the palm with a frictionless grace. However, gallium also possesses a wetting property on human skin and glass. As the liquid moves, it leaves behind a thin, grayish-silver stain, a metallic residue that is only a few atoms thick. This occurs because the gallium reacts with the trace amounts of oxygen and moisture on the skin to form a microscopic layer of gallium oxide, which acts as a lubricant and a pigment simultaneously. The most famous application of this thermal instability is found in the classic chemistry prank involving gallium spoons. In this scenario, a utensil is cast from pure gallium using a silicone mold, resulting in a spoon that is indistinguishable from standard stainless steel in terms of weight, luster, and rigidity. However, the moment this spoon is used to stir a cup of hot tea or coffee, liquids typically maintained at 150 degrees Fahrenheit, the structural integrity of the object vanishes instantly. To an observer, the spoon appears to simply evaporate into the liquid, leaving the user holding nothing but the handle. This is not a chemical dissolution. The gallium does not disappear into the H2O like sugar or salt. Instead, it undergoes a rapid phase transition, melting into a heavy, liquid pool that sinks to the bottom of the cup due to its high density of 5.91 grams per cubic centimeter. Because gallium is non-toxic and has a very low vapor pressure, it does not contaminate the drink, but it serves as a startling reminder that our assumptions about the permanence of metal are entirely dependent on a narrow window of temperature. One of the most peculiar engineering anomalies of gallium is its behavior during the reverse process, solidification. Most materials in the universe, including almost all metals, contract and become denser when they freeze from a liquid to a solid. Their atoms pack closer together as they lose kinetic energy. Gallium is one of the rare exceptions to this rule, joining H2O and bismuth in a category of substances that expand upon freezing. When liquid gallium transitions back to a solid state, its volume increases by 3.1%. This expansion is a result of the unique diatomic pairing mentioned previously. As the atoms reorganize into their complex orthorhombic lattice, they push away from one another to create the necessary gaps for their specific atomic handshake. From an engineering perspective, this expansion is a significant hazard. If liquid gallium is stored in a rigid glass or metal container and then allowed to cool below 85 degrees Fahrenheit, the force of its expansion is sufficient to shatter the vessel. To explain this on the fingers, it is exactly the same process that causes a glass bottle of soda to explode in a freezer, or a copper pipe to burst during a winter freeze. To store gallium safely, it must be kept in flexible polyethylene containers that can stretch as the metal solidifies. This buoyant property of the solid metal, where it is less dense than its liquid form, is a structural signature of an element that refuses to follow the standard blueprint of the metallic world. Another extraordinary characteristic of the 31st element is the phenomenon of supercooling. Under certain conditions of high purity, liquid gallium can remain in a fluid state even when the temperature drops far below its freezing point, sometimes reaching as low as 32 degrees Fahrenheit, or even the temperature of dry ice. This happens because the gallium atoms require a nucleation site, a microscopic impurity or a physical shock, to begin the process of organizing into a crystal. Without this trigger, the atoms continue to slide past one another in a disorganized liquid state, unaware that they should be a solid. To explain this on the fingers, it is like a car engine that is primed and ready to start, but lacks the spark to ignite the fuel. The second a tiny crystal of solid gallium is introduced to this supercooled liquid, a chain reaction occurs. The seed crystal provides the template, and the liquid metal freezes instantly, releasing its stored latent heat and returning to a solid state in a matter of seconds. The ghostly nature of gallium is further emphasized by its relationship with electricity and magnetism. Gallium is a diamagnetic material. meaning it is weakly repelled by a magnetic field. It also possesses a relatively low electrical resistivity for a liquid, which has led to its use in the creation of liquid wires and flexible electronics. Because it remains a fluid at room temperature when alloyed with indium and tin, a mixture known as gallium, it can be used to create circuits that can be stretched, folded, and twisted without breaking. This is the foundation of the emerging field of soft robotics and wearable technology. We are moving away from a world of rigid copper circuits and toward a world of metallic blood, where the electrical signals of a machine are carried by a flowing, silver-white metal that mimics the flexibility of biological systems. To look at a piece of gallium is to see a material that has abandoned the egoism of traditional metals. It does not demand the extreme energy of a blast furnace to be reshaped. It simply requires the proximity of a living being. It is a metal that functions as a bridge between the solid and the fluid, the macro world of tools and the micro world of atomic vibration. Every shimmering bead of liquid gallium is a testament to the fact that the most powerful materials in our inventory are not always the ones that are the hardest to break, but those that are the most responsive to the environment. The steel ghost that melts in the hand is a reminder that in the universe of the elements, the rules are often as fluid as the materials themselves. Gallium remains the ultimate prankster of the laboratory, a substance that teaches us to scrutinize our reality, proving that even a solid bar of metal can be as ephemeral as a shadow if given the right amount of warmth. It is the architect of the invisible, a material that allows us to manage energy with a precision that was once thought impossible, all while remaining humble enough to disappear in a cup of tea. The distribution of matter throughout the observable universe is governed by a rigorous chemical hierarchy, where the most essential structural elements are produced in vast quantities, while others remain as rare, high-energy leftovers of stellar evolution. Within this cosmic inventory, the 31st element, gallium, occupies a position of profound scarcity. To trace the biography of a single gallium atom, one must look past the stable, rhythmic fusion that powers a star like the Sun, and into the frantic, high-pressure environments of red giants and the catastrophic terminal spasms of supernovae. While common elements like carbon and oxygen are the mass-produced output of the celestial furnace, gallium is the result of a specialized and infrequent nuclear pathway known as the S process, or slow neutron capture. This process occurs over thousands of years within the interior of aging stars, where iron nuclei act as seeds that gradually absorb stray neutrons. Each capture event increases the atomic mass of the nucleus, slowly pushing the element up the periodic table until it reaches the specific configuration of 31 protons. This nuclear assembly line is characterized by a fundamental law of physics known as Harkin's rule, which dictates that elements with even atomic numbers are significantly more stable and abundant than those with odd atomic numbers. Because gallium possesses an odd number of protons, it is inherently less likely to be produced and more likely to be consumed by secondary nuclear reactions. In the grand ledger of the cosmos, for every gallium atom created, there are thousands of atoms of its neighbors, silicon and iron. It is a '17 a material produced in the narrow margins of stellar middle age, making its presence on a terrestrial planet a matter of extreme statistical luck. When these aging stars eventually shed their outer layers or collapse in a supernova explosion, the gallium is scattered across the interstellar void as microscopic dust, drifting for eons as part of the molecular clouds from which new solar systems are born. The arrival of gallium on the infant Earth, approximately 4.6 billion years ago, was governed by a sequence of gravitational and chemical sorting processes that defined the planet's internal architecture. During the '18, when the Earth was a roiling sphere of liquid fire, the heaviest and most '19 elements sank toward the center to form the core. Gallium possesses a dual chemical personality. It is both siderophilic, meaning it has an affinity for iron, and lithophilic, meaning it readily bonds with the silicate rocks of the crust. This internal tug-of-war prevented gallium from being entirely swallowed by the Earth's core. While a significant portion did migrate to the center, a critical fraction remained trapped within the mantle and crust, eventually becoming part of the solid surface. However, the most extraordinary aspect of gallium's terrestrial existence is its lack of a __quote _20 __. Unlike iron, which forms massive mountain ranges of ore, or copper, which can be found in concentrated veins, gallium never exists as a primary mineral. It is a __quote _21 __ element, an atomic introvert that survives by camouflaging itself within the crystalline structures of more common metals. This phenomenon is a result of a specific geochemical coincidence involving aluminum. In the periodic table, gallium sits directly beneath aluminum, meaning both elements share an identical configuration of 3 valence electrons. More importantly, the size of a gallium ion is almost exactly the same as that of an aluminum ion. In the language of mineralogy, they are __quote _22 __. To explain this on the fingers, if the Earth's crust is a massive construction project where aluminum atoms are the standard bricks, gallium atoms are rare, custom-made bricks of the exact same dimensions but a different color. Because the Earth's chemical processes cannot distinguish between the two based on size or bonding potential, the gallium atoms are mistakenly incorporated into the lattice of aluminium ores. Gallium spends millions of years acting as a chemical stowaway, hidden inside minerals like bauxite and sphalerite. This is why human civilization remained entirely unaware of gallium's existence until the late 19th century. We were building our world with aluminium and zinc, unaware that a steel ghost was riding along in every ton of ore we processed. The concentration of this stowaway into a mineable resource is a secondary process of extreme geological patience, driven by the relentless cycle of H2O and tropical weather. In the equatorial regions of the planet, where rainfall is heavy and the temperature remains high, the Earth's crust undergoes a process of intense leaching. As acidic rainwater filters through the soil, it dissolves the more mobile elements, like sodium and potassium, washing them away into the rivers and eventually the sea. Aluminum and its hidden partner, gallium, are highly insoluble in these conditions. They remain behind, becoming increasingly concentrated in the top layers of the soil to form a thick, reddish crust known as bauxite. This is a planetary-scale distillation, where the Earth uses its own weather patterns to vacuum the trace elements from the rocks and deposit them in concentrated vaults. Even in these enriched deposits, gallium remains a minority participant, typically appearing in concentrations of only 50 parts per million. To extract a single kilogram of gallium, modern industry must first process nearly 20 tons of aluminium ore. The industrial extraction of gallium is, therefore, a parasitic endeavor, relying entirely on the causal chain of the aluminum industry. The process begins with the Bayer process, a feat of high-pressure chemical engineering where crushed bauxite is dissolved in a hot solution of sodium hydroxide at temperatures exceeding 300 degrees Fahrenheit. Because gallium mimics the chemistry of aluminium so perfectly, it also dissolves into the caustic liquid, creating a pregnant liquor rich in both metals. To separate the twin elements, engineers utilize the subtle differences in their electrochemical potential. In a specialized electrolytic cell, a massive current is passed through the liquid. Because gallium is slightly less reactive than aluminium in this specific environment, it can be teased out of the solution first, often using a mercury cathode to capture the gallium atoms into a liquid alloy. This separation is an exercise in extreme precision. If the voltage is too high, the aluminium will precipitate as well, contaminating the product. If it is too low, the gallium will remain trapped in the liquid. The pure gallium that eventually emerges is a product of high-energy intervention, a material that has been forcibly separated from its chemical twin after eons of shared existence. We are essentially sieving the entire crust of the planet, using electricity to find the rare noble atoms that the Earth's gravity and chemistry almost lost. The cost of this process is high, both in terms of energy and the volume of waste generated, which ensures that gallium remains a strategic and expensive resource, reserved for the most advanced applications of the digital age. The cosmic accident of gallium is thus a story of a material that survives the high-energy birth of the universe and the gravitational sorting of a forming planet by pretending to be something else. It is a material that arrived as an afterthought in the planetary assembly, a precious ballast hidden in the rocks, waiting for a civilization that would finally develop the chemical and electrical tools required to see past its disguise. Every shimmering bead of gallium in a modern laboratory is a survivor of a sequence of events so improbable that its existence can be viewed as a thermodynamic miracle. It navigated the light years of the void as dust, escaped the iron abyss of the Earth's core, and survived the leaching of tropical rains by clinging to the quote, 31 of the crust. To look at gallium today is to recognize a guest from the deep past that has finally found its purpose in the high-tech future. We do not find gallium by looking for quote, 32 We find it by looking for the subtle imperfections in our more common resources. It is the element of the quote, 33 the substance that proves that the most powerful forces in our world are often those that hide in plain sight, protected by the very laws of atomic symmetry that make them so difficult to isolate. This cosmic heritage ensures that whenever gallium is used, whether in a high-speed charger or a satellite's laser, it carries with it the structural integrity of the stars and the hidden persistence of the Earth's geology. It is a material that transitions from the heart of a dying giant to the palm of a human hand, remaining a steel ghost that teaches us that even the most rare and elusive elements can be tamed if we learn to speak the language of their atomic connections. The gallium in our world is a permanent reminder that the architecture of our high-tech reality is built upon the captured remnants of a celestial chaos that occurred long before the sun ever shone. A material that refused to be left behind and found a way to hitchhike its way into the 21st century. The formal entry of the 31st element into the human scientific inventory represents the first great triumph of predictive chemistry, a moment where the mathematical laws of the universe were proven to be more reliable than direct physical observation. This historical drama began in 1869 within the cluttered, paper-filled study of the Russian chemist Dmitry Mendeleev. At this time, the periodic table was not the completed foundational chart found in modern classrooms, but a radical and controversial hypothesis. Mendeleev had organized the known elements by their atomic weights and chemical behaviors, but in doing so, he encountered a series of structural voids. One of the most prominent gaps existed directly beneath aluminium. Rather than assuming that his system was flawed, Mendeleev made a leap of logic that fundamentally altered the course of science. He insisted that the gap was not an error of classification, but a placeholder for an undiscovered material. He referred to this ghost element as eka-aluminum, utilizing the Sanskrit prefix eka to signify its position as the first neighbor to a known element. The engineering of Mendeleev's prediction was characterized by a level of precision that bordered on the supernatural. Based solely on the periodic rhythms of the elements surrounding the gap, aluminum, indium, and zinc, Mendeleev calculated the physical and chemical profile of a substance he had never seen. He predicted that eka-aluminum would have an atomic weight of approximately 68, a density of 5.9 grams per cubic centimeter, and a melting point so low that it would approach the temperature of a summer afternoon. To explain this on the fingers, Mendeleev was like an architect looking at a half-finished apartment building. Even though the fourth floor was missing, he could accurately calculate how much the future windows would weigh and what the internal temperature of the rooms would be, based entirely on the structure of the floors above and below. For 6 years, this detailed blueprint existed only on paper, a theoretical phantom that the scientific community treated with significant skepticism. The physical realization of this prophecy occurred in 1875, within a private laboratory in Paris belonging to the French chemist Paul-Émile Lecoq de Boisbaudran. Lecoq was an expert in the emerging field of spectroscopy, a discipline that treats light as a carrier of chemical information. To understand the mechanism of his discovery, one must view the spectroscope as a device for reading the invisible barcodes of matter. Every element, when heated to a gaseous state, emits light at very specific, unchangeable frequencies. By passing this light through a glass prism, the light is bent and separated into a series of distinct colored lines. Lecoq had spent years analyzing a sample of zinc blende, or sphalerite, extracted from the Pierrefitte mine in the Pyrenees Mountains. He was searching for hidden elements by observing the unique spectral signatures that appeared when the mineral was subjected to an electric spark. On August 27, 1875, Lecoq observed a phenomenon that shattered the existing chemical inventory. Within the spectrum of the zinc ore, a new and brilliant violet line appeared at a wavelength that did not correspond to any known substance. This was the first shriek of the 31st element, a signal from the atomic level that a new material had been found. However, the physical isolation of the metal proved to be an ordeal of industrial-scale patience. Because the concentration of the element in the zinc ore was so minute, Lecoq was forced to process nearly 4,000 kilograms of raw mineral to produce just a few grams of the pure metal. This was a process of chemical reduction involving acid baths and the application of high-voltage electricity to a solution of the ore. When the first beads of the metal finally emerged, they possessed the silver-white luster of polished steel, but exhibited a behavior that confounded the French scientist. The metal would spontaneously liquefy if the laboratory became too warm. Lecoq named the new element gallium, officially stating that the choice was a tribute to his homeland, as Gallia is the Latin name for France. This followed the established tradition of naming new discoveries after the nationality of the discoverer. However, this nomenclature immediately triggered a high-stakes drama of linguistic interpretation and personal ego within the international scientific community. In the French language, Lecoq translates to the rooster. In Latin, the word for rooster is gallus. Almost immediately, rumors began to circulate that the French chemist had performed a masterclass in clandestine self-immortalization, embedding his own name into the periodic table under the guise of national pride. Lecoq de Boisbaudran spent the remainder of his professional life vigorously denying these allegations, insisting that the link between Gallus and his surname was a purely accidental coincidence of etymology. Despite his denials, the ironic label of the Rooster metal remained a permanent part of the element's historical lore, a reminder that the naming of matter is often as much about human identity as it is about physical reality. The drama intensified when Mendeleev, reading of the discovery in a Russian journal, realized that the gallium of Lecoq was the eka-aluminum of his own 1869 blueprint. However, upon reviewing Lecoq's initial data, Mendeleev noticed a significant discrepancy. Lecoq had reported the density of the new metal to be 4.7 grams per cubic centimeter. Mendeleev, writing from thousands of miles away in St. Petersburg, sent a letter to the French laboratory correcting the discoverer's own measurements. He insisted that Lecoq must have miscalculated or that the sample was impure, as the laws of the periodic table demanded a density of 5.9 grams per cubic centimeter. To explain this on the fingers, it was the ultimate confrontation between the map and the territory. Mendeleev was arguing that the physical reality of the metal must conform to the mathematical laws of the table. Lecoq, initially offended by the suggestion that a theoretical chemist who had never touched the metal could know its properties better than the man who had isolated it, returned to his laboratory to perform a more rigorous purification. After removing the last traces of zinc and indium from his sample, Lecoq re-measured the density. To his astonishment, the value rose to exactly 5.91 grams per cubic centimeter. The steel ghost had finally aligned with its mathematical shadow. This verification was a watershed moment for modern chemistry. It proved that the periodic table was not merely an organizational convenience, but a deep, predictive law of nature. Gallium became the primary witness that validated the entire concept of elemental families, turning Mendeleev from a speculative theorist into a scientific prophet. The historical trajectory of gallium continued to be defined by its invisible utility throughout the late 19th and early 20th centuries. Because the metal was so rare and expensive to extract, it remained a laboratory curiosity, a material used by physics teachers to demonstrate the bizarre phenomenon of a metal that could melt in a human hand or expand upon freezing. It was a trick metal, used to craft the disappearing spoons mentioned in the previous section, serving as a medium for scientific entertainment rather than industrial infrastructure. It was not until the development of the vacuum tube and early radio technology that engineers began to look at gallium for its thermal and electronic characteristics. The transition from a Rooster metal to a high-tech engine was delayed by the sheer difficulty of finding a concentrated source. Throughout the early 1900s, gallium was identified as a trace impurity in coal ash and flue dusts, leading to a period of parasitic mining, where chemists would sift through the waste of the steel and coal industries to find a few milligrams of the 31st element. This era of history reflects the element's inherent introversion. It is a material that has never sought the spotlight, preferring to remain a hidden stabilizer within the ores of more common metals. It was a substance of latent potential, waiting for the era of the electron and the photon to find its true purpose. To look at the history of gallium is to see the birth of the precision era in science. We moved from the era of alchemy, where materials were found by chance, to the era of Mendeleev, where materials were searched for because their existence was a logical necessity. Gallium was the first material to be summoned into existence by human mathematics. It is a metal that forced the world to recognize the internal rhythm of the atom, proving that the properties of matter are not random, but are dictated by a rigorous underlying order. The historical drama of gallium is the story of how a steel ghost was identified in the sun's light and the zinc's shadow, and how it eventually settled the dispute between the French Rooster and the Russian prophet. It remains a material that bridges the gap between the 19th century laboratory of acid and glass and the 21st century cleanroom of lasers and silicon, a shimmering silver-white thread that connects the first dreams of the periodic table to the high-speed reality of the present. Every time we utilize the magic of a material that responds to the heat of a touch, we are benefiting from a century-long struggle to prove that the universe follows a blueprint and that gallium is one of its most essential and accurately placed bricks. The physical landscape of the 21st century is defined by a relentless demand for electrical efficiency and extreme miniaturization. The era of silicon, which dictated the boundaries of computing and power management for over 50 years, is currently encountering its fundamental physical limits. As engineers attempt to force increasingly massive amounts of electrical power through progressively smaller silicon components, the resulting subatomic friction manifests as destructive thermal energy. The solution to this thermodynamic bottleneck is found in the 31st element, specifically when bonded with nitrogen to form the compound gallium nitride. This material has quietly initiated a total restructuring of modern electronics, serving as the invisible engine that allows our devices to operate at speeds and power densities that would cause traditional silicon architecture to melt into useless slag. To understand the mechanical superiority of gallium nitride, one must analyze the function of a standard power supply or charging adapter. Its primary role is to take high-voltage alternating current from a wall outlet and convert it into a steady, low-voltage direct current that a laptop or smartphone can safely consume. This conversion requires a series of internal transistors to act as gates, opening and closing millions of times per second to chop and regulate the electrical flow. In a silicon-based transistor, this switching process is fundamentally inefficient. Every time the gate opens or closes, electrons encounter resistance as they cross the semiconductor threshold, releasing a significant portion of the electrical energy as waste heat. To prevent the charger from overheating and catching fire, it requires large, bulky aluminium heat sinks and heavy copper coils. These thermal management components dictate the heavy, brick-like dimensions of older adapters. Gallium nitride completely circumvents this architectural requirement through a quantum mechanical property known as a wide band gap. In the mechanics of a semiconductor, a band gap is the specific amount of energy required to free an electron from its home atom so it can move through the material and conduct electricity. To explain this on the fingers, if a standard silicon transistor is a narrow, unpaved road where electrical traffic is forced to slow down and constantly bump into obstacles, generating heat and friction, a gallium nitride transistor is a wide, perfectly smooth, high-speed rail line. The wider bandgap allows the material to sustain much higher electrical voltages and operating temperatures before the flow of electrons becomes chaotic or breaks down. Furthermore, electrons move through the gallium nitride crystalline lattice with a mobility that is vastly superior to their movement in silicon. Because this high-speed switching process generates almost zero waste heat, the massive cooling blocks can be entirely eliminated from the design. The result is a charging device that is half the physical size of its predecessors, yet capable of delivering 3 times the power. Gallium is the material that untethered the modern workforce, providing the dense, rapid bursts of energy required to keep lithium-ion batteries functioning without weighing down the user with heavy thermal baggage. This efficiency scales up to the massive data centers that power cloud computing and artificial intelligence. These server farms consume electricity on the scale of small nations, and if silicon were the only material available, the cooling systems required to prevent the servers from melting would be economically and physically unsustainable. Gallium nitride allows these global power management systems to shrink in size and run cold, acting as the thermal savior of the digital expansion. The utility of gallium extends far beyond the invisible management of power, serving as the absolute foundation for the generation of artificial light in the modern era. The transition from the warm, inefficient glow of incandescent bulbs to the brilliant, energy-efficient illumination of the contemporary city rests entirely upon the atomic geometry of the gallium nitride crystal. For decades, engineers could easily manufacture light-emitting diodes that produce red and green light. But the creation of a blue LED remains one of the most profound physics problems of the late 20th century. To produce blue light, which carries significantly more energy and possesses a shorter wavelength than red or green light, a semiconductor must possess a very specific, wide energy band gap. The 31st element provided the exact atomic architecture required to bridge this gap. Before gallium nitride, human lighting was a brute force exercise. Tungsten wire was heated until it glowed white hot, wasting 90% of the electricity as thermal energy. The creation of the gallium-based blue LED changed this fundamental dynamic. The crystalline structure of gallium nitride had to be grown with 0 defects, a process that defied metallurgists for decades because the atoms refused to align properly on standard substrates. When engineers finally forced the gallium and nitrogen atoms into a perfect, defect-free Wurtzite crystal lattice, they unlocked the ability to generate blue photons. When a carefully calibrated electrical current is passed through this microscopic chip of gallium nitride, the electrons are elevated to a higher, unstable energy state. As they inevitably drop back down to their stable ground state, they release the exact amount of excess energy required to emit a brilliant blue photon. This blue light was the missing foundational piece of the modern optical world. By coating a blue gallium nitride LED in a microscopic layer of yellow phosphor, the sharp blue light mixes with the yellow emissions to produce the pure, bright white light that currently illuminates homes, offices, and automotive headlights across the globe. This single application of gallium has reduced global lighting energy consumption by massive margins, rendering the heat-wasting filaments of the past obsolete. The same blue photons generated by gallium are responsible for the high-definition physical media and data storage systems of the present day. In a Blu-ray player or a high-capacity optical drive, a gallium nitride laser emits a beam of blue light that is focused into an impossibly sharp point. Because blue light possesses a significantly shorter wavelength than the red light used in older DVD and CD technology, the laser can read data pits on the surface of a spinning plastic disc that are packed much closer together. To explain this on the fingers, using a red laser to read a disc is analogous to trying to paint fine details with a thick, blunt brush, whereas using a gallium-based blue laser is equivalent to drawing with an ultra-fine precision pen. This allows a single disc to hold 5 times the amount of information, facilitating the storage of high-definition video and massive corporate datasets. Gallium is the material that sharpens the optical needle of the digital age, allowing humanity to write and read information at a density previously thought to violate the laws of optics. However, the unparalleled utility of gallium in the digital and optical realms is counterbalanced by a dark, destructive capability in the physical world. Specifically, its lethal chemical interaction with the primary metal of global aviation. Aluminium is the unquestioned backbone of the aerospace industry, a metal that derives its durability from a tight, interlocking crystalline lattice. The individual microscopic grains of aluminium are bound together by intense metallic forces, creating a rigid structure capable of withstanding the immense aerodynamic pressures of flight at 600 miles per hour and temperatures dropping to -60 degrees Fahrenheit. Furthermore, aluminium protects itself from corrosion by instantly forming a tough, microscopic shield of aluminium oxide whenever it is exposed to the air. Gallium acts as the ultimate structural disruptor, a substance that operates as literal kryptonite for this aviation infrastructure. If a single drop of liquid gallium at a standard room temperature of 75 degrees Fahrenheit is placed onto a sheet of structural aluminium, a silent and catastrophic process known as liquid metal embrittlement begins immediately. The gallium does not dissolve the aluminium like a traditional acid. Instead, it performs a highly targeted subatomic infiltration. The liquid gallium atoms first breach the protective aluminium oxide layer, preventing the aluminium from maintaining its chemical shield. Once past the armor, the gallium exploits the microscopic boundaries between the individual aluminium grains. To explain this on the fingers, a massive, load-bearing brick wall where the solid mortar holding the bricks together is suddenly and silently replaced by slippery, liquid soap provides a perfect analogy. The individual bricks themselves remain entirely intact and undamaged, but the wall instantly loses all of its structural integrity and cohesiveness. The gallium atoms, existing in their fluid, chaotic state, migrate rapidly down into the crystalline grain boundaries of the solid aluminium. They disrupt the metallic bonds that hold the aluminium grains together, replacing those rigid connections with a weak, brittle gallium-aluminium amalgam. This process does not require high heat or external pressure. It spreads through the solid metal like an invisible, high-speed rot, driven purely by capillary action and thermodynamics, deep into the heart of the structure. Within a matter of hours, a solid aluminium beam that could previously support the weight of a heavy commercial aircraft undergoes a total and irreversible loss of mechanical strength. The gallium atoms wet the grain boundaries of the aluminium, lowering the surface energy required for a crack to propagate. When a mechanical stress is applied, the crack shoots through the gallium-infiltrated boundaries at the speed of sound. A person can simply reach out and snap the thick metal beam with two bare fingers, breaking it apart as easily as a dry, crumbly cookie. The metal fractures along the compromised grain boundaries with a dull, sickening crunch, exposing a grey, granular interior where the gallium has severed every structural connection. During this process, because the aluminium is stripped of its protective oxide layer, it also begins to react violently with ambient moisture, or H2O, in the air, generating heat and releasing hydrogen gas while it crumbles into useless dust. This silent, room-temperature destruction is the precise reason why gallium is classified as a severe hazardous material by global aviation authorities, strictly banned from being transported in passenger aircraft cabins or unsealed cargo holds. A small vial of liquid gallium, if accidentally spilled onto the floor of an airplane, could theoretically seep through the carpets and come into direct contact with the aluminium floorboards or the pressurized fuselage shell. The resulting liquid metal embrittlement would compromise the aircraft's ability to maintain cabin pressure or survive the massive aerodynamic stresses of flight, leading to a catastrophic mid-air structural disintegration. A wing that is designed to flex and bounce gracefully in turbulence would instead shatter like glass under the same conditions. The element that allows the passengers to charge their electronic devices faster and read their glowing screens with brilliant clarity is the exact same element capable of turning the massive vehicle carrying them into a fragile, crumbling ruin. Gallium demands absolute respect for its dual nature. It is the supreme architect of the digital flow, directing electrons and photons with unmatched precision, while simultaneously serving as the silent executioner of the physical world's most trusted structural metal. It forces modern engineering to balance the brilliant efficiency of its semiconductor applications against the terrifying reality of its liquid state, proving that the most advanced tools of our era are often those that hide the most uncompromising and destructive physical traits. Without the constant, silent work of this metal magician, the modern world would be significantly heavier, hotter, and slower, trapped by the limitations of silicon and the inefficiency of incandescent light. The long-term legacy of human civilization upon the geological record of the Earth is dictated by the relentless and uncompromising laws of chemical entropy. The planetary surface operates as a highly efficient recycling mechanism, a continuous thermodynamic engine driven by the corrosive presence of oxygen, the universal solvent properties of H2O, and the grinding friction of tectonic movement. When evaluated across a timeline of millions of years, the vast majority of the physical infrastructure that defines the modern era is destined to undergo a total structural collapse and elemental dispersal. The towering frameworks of carbon steel that form the skeletons of contemporary megacities will inevitably react with atmospheric moisture, succumbing to oxidation and returning to the soil as diffuse, unstructured streaks of orange iron oxide. The complex synthetic polymers that constitute the bulk of consumer plastics will be degraded by the unyielding bombardment of ultraviolet radiation from the sun and the slow, adaptive metabolism of specialized microorganisms, eventually breaking down into simple hydrocarbon chains. Even the monumental concrete foundations of hydroelectric dams and subterranean bunkers will be slowly dissolved by the faint presence of carbonic acid in global rainfall, reverting to an amorphous dust of calcium and silica. However, within this landscape of inevitable decay, the 31st element provides a permanent, crystalline exception, securing a legacy of endurance that defies the transient nature of the civilization that refined it. The survival of gallium in the deep geological future is not a function of its pure metallic state, which, as previously established, possesses a thermal threshold so fragile that it liquefies at a mere 85.57 degrees Fahrenheit. Instead, its permanence is guaranteed by the specific industrial metamorphoses it undergoes to fulfill its role as the high-speed engine of the digital age. To harness the electronic capabilities of gallium, modern engineering forces the element into a state of extreme chemical discipline, bonding it primarily with nitrogen to form gallium nitride, or with arsenic to form gallium arsenide. The creation of gallium nitride is a masterclass in the application of high-energy physics, requiring a manufacturing environment that essentially replicates the intense heat and pressure of a planetary interior. In specialized reactors, gaseous compounds carrying gallium and nitrogen atoms are subjected to a process known as metal-organic chemical vapor deposition. Through the precise manipulation of temperature and pressure, the gallium atoms are stripped of their liquid metallic identity and locked into a dense, interlocking wurtzite crystal lattice. The transition from a low melting point metal to a wide bandgap semiconductor represents one of the most drastic shifts in physical stability achievable in material science. The covalent bonds holding the gallium and nitrogen atoms together within this lattice are exceptionally strong, possessing a bond energy that renders the resulting crystal practically immune to standard environmental degradation. While pure gallium melts from the warmth of human skin, the synthetic gallium nitride crystal requires a temperature exceeding 4,500 degrees Fahrenheit to break its internal architecture. It is a material that has been engineered to withstand the extreme thermal loads of high-power electrical switching and the intense energy of blue laser emission. And this exact thermal resilience provides it with a geological immortality. It does not oxidize in the presence of air. It does not dissolve in H2O, and it is highly resistant to the corrosive acids that naturally occur in groundwater and soil. It is a synthetic rock of unparalleled perfection, designed to manage the flow of electrons with zero resistance, and in doing so, it inadvertently becomes an indestructible artifact. When projecting the trajectory of the Earth millions of years into the future, long after the cessation of all human industrial activity, the locations of present-day data centers and telecommunications hubs will become distinct stratigraphic markers. As the organic and ferrous components of these massive server farms rot and rust away, the dense clusters of gallium nitride processors and power adapters will remain perfectly intact. They will settle into the accumulating sedimentary layers of the planet, buried under meters of soil and rock. These microscopic, highly engineered chips will effectively become the techno-fossils of the digital epoch. For any future geological survey, whether conducted by an evolved terrestrial intelligence or a visiting extraterrestrial observer, these concentrated deposits of gallium compounds will stand out as glaring anomalies against the natural mineralogy of the Earth's crust. To a high-level scientific observer, a fossilized gallium nitride chip would not appear as a mere piece of stone, but as a densely coded physical document. The extreme purity of the crystal, combined with the deliberate atomic-scale doping of specific impurities used to tune its electrical conductivity, is a signature that cannot be replicated by any random geological or volcanic process. The precise, alternating layers of atoms, deposited with nanometer accuracy, serve as an unmistakable chemical autograph of a species that had achieved total mastery over the quantum mechanical properties of matter. The discovery of these crystals in the deep future will provide absolute proof that a civilization once existed capable of manipulating the band gap of rare elements to control the movement of light and electricity. Gallium will serve as the eternal, silent archivist of the era of ultra-fast charging networks and high-definition screens, preserving the evidence of our technological sophistication long after the screens themselves have shattered into meaningless silica dust. The legacy of gallium also extends outward into the most hostile environment accessible to human engineering, the hard vacuum of Earth's orbital space. The modern telecommunications grid is heavily reliant on a constellation of satellites occupying geosynchronous orbit, located approximately 22,236 miles above the equator. In this extreme environment, components are subjected to a continuous barrage of high-energy cosmic rays, solar flares, and wild temperature fluctuations that swing from 250 degrees Fahrenheit in direct sunlight to negative 250 degrees Fahrenheit in the Earth's shadow. Traditional silicon-based electronics are highly vulnerable to this radiation, as the high-energy particles easily knock silicon atoms out of their lattice, causing the processes to degrade and fail over time. To ensure the survival of critical communication systems and solar panel arrays, aerospace engineers turn to gallium arsenide and gallium nitride, materials that possess an inherent radiation hardness. The dense, heavily bonded atomic structure of these gallium compounds allows them to absorb the impact of cosmic radiation without suffering the catastrophic lattice dislocations that cripple lesser materials. Because the vacuum of space lacks the atmospheric drag that pulls low-orbiting objects back down to burn up in the Earth's atmosphere, satellites in geosynchronous orbit are destined to remain in their positions for millions, if not billions, of years. They occupy a region of absolute silence and stillness, effectively becoming permanent, orbiting monuments to the aerospace era. The lightweight aluminium and carbon fiber chassis of these satellites will slowly degrade under the relentless ultraviolet bombardment of the sun, and the plastic insulation will eventually turn to brittle dust. However, the gallium-based amplifiers and solar cells will endure. They will continue to exist in a state of chemical perfection, drifting through the dark void long after the radio signals they were built to transmit have ceased. These orbiting gallium crystals represent the highest physical elevation of human achievement, a rare elemental stowaway that was carried from the deep crust of the planet into the permanent, freezing archive of the cosmos. The ultimate fate of the 31st element is deeply intertwined with the life cycle of the solar system itself. In roughly 5 billion years, the Sun will exhaust its primary supply of hydrogen fuel and enter the red giant phase of its stellar evolution. As the Sun's outer layers expand to engulf the inner planets, the surface temperature of the Earth will climb to levels that rival the interior of an industrial blast furnace. The oceans will boil away into space, and the silicate rocks of the crust will melt into a global sea of churning magma. It is only under these apocalyptic conditions that the legacy of the gallium nitride crystals will finally be erased. The intense stellar heat will provide the immense kinetic energy required to shatter the indestructible covalent bonds holding the gallium and nitrogen atoms together. The eternal techno-fossils buried in the ruins of our data centers, as well as the radiation-hardened chips orbiting above, will finally melt and vaporize. The gallium atoms will be liberated from the crystalline prisons constructed by human engineers. As the Earth is consumed by the expanding solar atmosphere, these atoms will be ejected back into the interstellar medium. They will return to the vast, drifting clouds of cosmic dust, reverting to the same state they occupied billions of years ago after being forged in the slow neutron capture of a dying star. The gallium will lose all structural memory of the smartphones, lasers, and satellites it once inhabited, becoming a solitary, unbonded metal once again. It will travel through the cold vacuum of the galaxy, waiting for the gravitational collapse of a new nebula to draw it into the formation of a different world. In the grand accounting of the periodic table, gallium represents the ultimate physical paradox, a substance that bridges the extremes of fragility and permanence. It is a material that was historically treated as an elaborate laboratory prank, famous for its inability to maintain a solid form in the gentle warmth of a human hand. Yet, through the application of precise thermodynamic engineering, this exact same element was transformed into the most unyielding and durable semiconductor in the human inventory. It is the metal that allowed civilization to compress massive amounts of power into microscopic spaces, enabling the high-speed, brightly illuminated reality of the modern day. The story of gallium is the story of how a homeless, hidden impurity found within common aluminum ore was extracted, purified, and elevated to become the final, indestructible witness to the human epoch. When the final history of the Earth is analyzed, it will not be the heavy iron or the brilliant gold that provides the most detailed record of our technological peak. It will be the rare, silver-white element that learned to hide inside an eternal crystal, silently holding the architecture of the digital age intact against the relentless crushing weight of deep geological time.